So thanks everybody for joining us today. Before we get started, I wanted to do a little bit of a sad announcement for people who may not know. Member of our community recently passed away on March 30th, and I know a lot of people knew Jim Warner. He gave several talks within the CI engineering community over the past couple of years, and for those of you that did know Jim, he was just an all-around great guy. Could converse for hours on anything technical. Could certainly give you lots of advice after his 41 years of experience in the networking field. I met him originally when I was still a young pup coming up through University of Delaware and Internet 2. And he was an early adopter and full supporter of Perf Sonar when he was with University of California, Santa Cruz. And most other people may know him via the website repository that he maintained of performance behaviors for network devices. It's a great loss to the community, and certainly he's going to be missed by everyone. His family has recommended that if anybody does feel strongly about honoring some of Jim's memories, consider giving charitable donations to a couple of things that may be near and dear to your heart. In particular, they've been supporters of Second Harvest and American Red Cross, local animal shelters, Doctors Without Borders, and public radio. But we did want to sort of call this out since a lot of people may not have heard this announcement quite yet. And certainly we're all going to miss Jim. So that's my little start to this today. And certainly we don't want to start things and keep it on a sour note. He was certainly a great champion of this community, and we'll miss him. One of the reasons that we wanted to say that is because the topic today that we're going to be going over is probably something that would have been very near and dear to Jim's heart. It's a pleasure to welcome back the great team from University of South Carolina, who's done a lot of research in network performance and switching behaviors about how to support high performance data transfers. And Elie is going to be talking about some of his research today. It's an extension of some of the research and presentations that he and Jorge have presented in the past, focusing a little bit on P4, but also just how to integrate this into modern networks, some of which may not be completely P4, completely controllable. So Elie, if you'd like to share, and I'll turn it over to you.
Yeah, and Jason, before we start, also, this is Jorge. I remember Jim because, as you very well said, we can trace back this presentation to Jim. So briefly, he helped many of us when we started working on Science DMC in my previous place that I used to work, Northern New Mexico College. The information in his website was very instrumental. So we designed the Science DMC back at Northern New Mexico College. We deployed the Science DMC. That was back in 2015, 16. And then many other small colleges use our model. So Jim has an impact on all these colleges in Northern New Mexico College. Today we will be talking more precisely, Elie will be talking about router buffers and other topics, but router buffers can be traced back to Jim's website. So there is a website where Jim used to collect everything about buffers. So when we were building our Science DMC back at Northern New Mexico College, one of the deciding factors of which device should we buy was the buffer size. And since then, Northern New Mexico College and then University of South Carolina, when I moved to University of South Carolina, and grad students have been conducting research on buffer sizing and similar topics. So with this short note, we want to remember Jim and thank him for helping so many members of this community. With that, Elie, I will let you share the presentation and feel free to start.
All right, thank you. So hello, everyone. My name is Elie. I will be presenting today P4Tune, enabling programmability in a non-programmable network. So I'm at the University of South Carolina. I'm a PhD student working with Dr. Jorge Crichigno. So the agenda for this talk, first, I'm gonna go very briefly on non-programmable networks and the evolution of programmability in the network, which is basically the software-defined networking at P4. And then I will discuss some challenges to adopt these P4 switches into modern networks. And then we're gonna introduce P4Tune framework, which is basically a way that we can leverage these P4 switches and benefit from them without having to replace the whole infrastructure. And we're gonna demonstrate 4 use cases that follow this framework and discuss some results that we got so far. Current networks are basically using fixed function devices, and this has been the case since the explosive growth of the internet in the 90s. We would have a router with a fixed function ASIC. The control plane and the data plane are within the same unit, and the control plane will be running an algorithm to populate the data plane. And all the interfaces are proprietary. They are only known to the vendor. So this would put a lot of dependence on the vendor itself. And this prevented also the network owners to innovate more in that space. And then SDN came along, software-defined networking, to challenge this protocol ossification. And the idea is to separate the data plane from the control plane. We would have a control plane where we can develop some apps. It's going to be a centralized controller, and this control plane would be managing the data plane of multiple devices. SDN has a limitation, which is it's currently limited to what OpenFlow protocol supports. So the data plane are still fixed. We can't modify the packet processing there. And more recently, P4 emerged. P4 is a technology that allows the operator to program the data plane of the device. And therefore, we can define and parse new protocols. We can devise some custom algorithms that will run at line rate at the data plane. And the switch would provide us with a very granular and high precision timer, so we can measure events that happens very fast and take some actions. And with all these reasons, we've seen in the past few years a lot of applications being offloaded from general purpose servers to the data plane. P4 is just the language that we use to program these data planes. It's high level. You just describe what the packet processing would look like. You compile it, and then you push it to the programmable ASIC. There are some deployment challenges that we've seen when we deal with P4. First, the operators lack the programmability knowledge of the data plane, and the reason is most of the common networks nowadays have these legacy devices, and operators would typically just configure them. For example, modify some routing configuration, update an access control list or ACL, and also programming P4 for the target is very complex. There's this program, switch.p4. It contains the basic switch capabilities of a layer 2 and layer 3 switch. And this program itself has a lot of control paths, which makes it very complex to be programmed. And also, the networks would have an existing infrastructure, and there was a significant cost, time, and effort spent in building that infrastructure. And so replacing all of these with P4 switches would incur significant costs. Another point is the vendor support. So currently you can get support from the device vendors for the legacy routers. I'm calling legacy routers and switches for all these devices that we find in current networks. But P4 switches, on the other hand, are white boxes. So we have little to no support from the vendors. And finally, there is always this risk of disrupting the network because we are programming the data plane, and there might be some potential source of bugs that we have in our program that can affect the whole network. It can potentially disrupt it and affect the availability of the services. And so with all this in mind, we started about thinking of an idea to leverage these P4 switches to gain some of their benefits, but also try to think in a cost-efficient way and see if we can use them in a way to improve the performance of the existing network. And so we came up with this framework or architecture. We called it P4Tune. You can see here in the figure, this is the forwarding, quality of service, access control layer. So this is pretty much where all the legacy devices are. Regardless of which topology you have, you might have some firewalls, you might have routers and switches, and all of these are the ones that you see in current networks. And what we can do is we can install optical taps on some links of this topology and connect links to programmable data planes. So the taps that are connected here, first we want to make sure that we only tap the links that we are interested in monitoring. So, and this depends on the application. If you want to do packet tracing all over your network, you want to make sure to select the vantage point to position these taps. And these taps will create the copy of the traffic, send them to the P4 switch without affecting any of the characteristics. So we would have the exact same copy. This means that the timing information, all of the characteristics that would define the traffic would remain the same. And in our data plane, we would be running some in-network applications. And here we can have a P4 switch, we can have a programmable NIC, we can have a net FPGA, but basically anything with a programmable data plane. And then next, this layer here will be communicating with another layer where we would have some intelligent algorithms residing on either a control plane of the switch or a dedicated server. And this is where we will be collecting the statistics, the measurements, sometimes some sampling of the packets. And then all of this information, we will be using them to basically create some configuration rules. These rules can be deployed to the legacy devices through some APIs, or it can be some configuration to change the state of the P4 program in the data plane. For example, if you are detecting heavy hitters, you might want to change the threshold, then you can have the control plane to modify some of the part of your program here in the data plane. Now, regarding this side here of the control, we can basically create rules that are in the form of ACLs, or it can be related to quality of service, and push them to that layer. And what we'll be gaining by doing so is that we are processing the traffic at line rate, doing custom packet processing, getting all the information that we want, and then try to come up with rules that can really affect the traffic flowing in our legacy network. Now, what we can do here with the control is kind of limited to what the device provides. But most of the core routers nowadays, they have a lot of quality of service features and integrated ACLs and filters for firewalls that allow us to do very interesting applications in these legacy devices. And if we look at it, this is kind of creating a loop for us, a control loop, where we are always getting this information, the statistics from the data plane, coming up with the configuration, and then pushing it to influence the new traffic that is flowing into our legacy network. So we developed 4 use cases so far. I'm going to describe some of them and show the initial results that we get. The first one is the dynamic buffer sizing. And we know that routers have memory, which we refer to as the packet buffer. And the size of this buffer would dramatically impact the performance of the network. If we decide to use large buffers, this is gonna introduce some delays. And this is known as the buffer bloat, where the flow completion time of short flows will be very large due to the large buffer that we have. But it would be good for long flows transferring data, for example, file transfer of very large files. On the other hand, if you decide to go with small buffers, then some packets will be dropped and you might have low link utilization. And finding the right size for that buffer is not an easy task. There has been some suggestions in the literature. The most known one is the rule of thumb, which is we set the buffer equals to the bandwidth delay product. And the bandwidth delay product here is the multiplication of the capacity of the link and the round trip time, specifically the average round trip time that we are seeing in the network. And then later on in 2004, there was this paper that showed that you can have much smaller buffers. You can have the bandwidth delay product divided by the square root of n. And n here is the number of long flows that are persistent over time, traversing your link. Now, if you want to apply the Stanford rule, and the Stanford rule refers to this one here, the idea is we need to determine the number of flows that are traversing our bottleneck link, and also we need to estimate the round trip time. And if we decide to do this in a general purpose CPU, we cannot cope with the high traffic rates. And if we decide to go for sampling techniques such as NetFlow, we'll end up having not enough accurate results. And there's this paper that basically showed the error of estimating the number of flows in a CAIDA data set by using the sampling technique. And we can see that the error is significantly large, that you cannot rely on it to use it as part of this formula to set your buffer size. And so what we developed here is a system that will leverage P4 switches to get the measurement from the legacy network and perform counting for the flows, for the large flows in the data plane, as well as computing the round trip time. So these two computations will happen at line rate. We will have these statistics ready for every packet that we receive on our P4 switch. Then the statistics will be pushed to the control plane, where we will be basically computing the buffer size. So here in this use case, we set the buffer equal to BDP over square root of n, which is the rule referred to as the Stanford rule. Once we know this buffer size, we can basically modify the actual buffer on the legacy router by having like a management link. So it's like a outbound connection that we use to modify this buffer size. And this is happening on the fly. So we keep measuring and then updating the buffer. For the implementation, so we have this topology. We have 200 senders and 200 receivers. We bridge them through a Novi S switch. And we use the Juniper MX204 as the router on the bottleneck because it has the capability of dynamically changing this buffer, the buffer size. And then we have a bottleneck link of 1 gigabits per second. And what we have here is a tap installed on both directions. And they are connected to our P4 switch, which is an edge core with the Intel Tofino chip. And we did the evaluation by generating traffic using iPerf. We use different congestion control algorithms. We've seen what is the most recently used congestion control on the internet, and we try to use this distribution to assess the performance of our system with these different diverse congestion control algorithms. And for the default buffer size, we use it equal to 200 milliseconds. So there's this nice paper by Professor McEwen that mentions that the router vendor suggested a buffer size approximately equal to 200 milliseconds. So we decided to compare this proposal against if we use just a static buffer of 200 milliseconds. So two scenarios are considered. This is the two that I was discussing, one with a static buffer and the other with a dynamic buffer based on our proposal. So we have multiple long flows that were initiated with different congestion control algorithms and different propagation delays. And we can see here in the table, in the RTT probe, these are the different propagation delay that we used. And you have different number of flows. These are these columns. And you have different congestion control algorithms. And even you have a mixed column, which basically mixes these congestion control based on the distribution that is available on the internet. And regarding the metrics, we evaluated the link utilization, the average link utilization, the fairness index, which tells us how fair our link was divided among the flows, and the average round trip time. So this round trip time here would include the queuing delay that was introduced because of the buffer. And this first part of it, the left-hand side, is with the static buffer. So without buffer modification, the right-hand side with buffer modification. First, we can see that for the link, we got pretty much very high link utilization, around 99%. And this is basically what was suggested whenever you use this Stanford rule. You would sacrifice like very small percentage of your link. The fairness was improved. We can see in most of the cases, we got better fairness index. And finally, for the round trip time, we got, of course, a lot of improvement. That's because the buffer is much smaller, and it means that the whole round trip time is going to be much smaller than when you have a large buffer that, you know, will basically queue these packets. And the nice thing to note is that even with a small number of flows, so if it is 50 or 200, we have the buffer being fully utilized, and that's because how the congestion control works. They keep pushing and having this AIMD, that additive increase, multiplicative decrease. So even with small number of flows, even if you have 2 or 3 flows, we would see a buffer being fully utilized and a round trip time increased. We also assessed the flow completion time and the round trip time of the short flows. So these were generated as well, 1,000 short flows. We specified their size to be from 10 kilobyte to 1 megabyte to resemble a web search workload. And we have 200 long flows running in the background with a propagation delay of 50 milliseconds. And what we can see here is that on the left-hand side here, you have the case without the buffer modification. You can see the round trip time are also high for the short flows. Whereas when we modify the buffer, they're all very short. And also this is shown in the flow completion time, because for these interactive short flows, basically you're sending a packet, and then if it is waiting longer in the queue, then it's going to take much longer for the whole flow to finish. And we've seen the improvement regardless of which congestion control algorithm that was used. So another use case that we studied was if we can separate the traffic based on the flow size. And the idea is, as we've seen in the previous use case, the flow completion time of the short flows would be significantly impacted when the network is busy. So is there a way that we can basically minimize this flow completion time in a busy network? A possible solution would be to separate our traffic into 2 queues. And the routers, the core routers nowadays have the classifier available. The most common classifiers available in commercial routers are what are known as behavior aggregate. This would look at some fields in the packet headers, for example, the SCP or the IP precedence. Or you can create like a firewall filter, and you decide which fields you want to match on. The issue with the first approach is that the DSCP fields are rarely being used. And there's this paper that did a study on Qaeda backbone, and it's seen that a very small percentage of the traffic had these quality of service fields there. And the problem of the second one is that usually operators would need to hard code these rules. And if you have a very dynamic network, a lot of traffic entering and joining, and you don't know their IPs, it can be very tricky to do the separation. And so what we propose is to have a P4 assisted flow classification. The idea is we can have a tap installed next to our non-programmable router, get the traffic, have P4 switch identify the large flow. In our implementation, we use the count-min sketch. This is a very well-known algorithm, streaming algorithm to identify large flows or elephant flows. And then based on that flow that we identified, we construct a 5-tuple firewall filter for that specific flow. And then we specifically send it to the multi-feed classifier to use a separate queue, which we are calling here the long flows queue. So all the regular traffic by default will go to the short flows queue. And if we've seen that one of the flows is a large flow, we immediately shift it to the long flow queue. So this way we are separating them, even if we don't know anything about the flow beforehand. So we are letting P4 completely know this characteristic of these flows and perform the traffic separation. We tested also with some generated data. We have 10,000 flows, short flows. And also we use the same distribution as before. We have 10 long flows starting at random starting time over the test duration, just to see how adaptive this algorithm is in pushing those rules to the legacy routers. So we made it in a way that they start completely different starting times and they're completely random. And we can see here the performance benefits that we got. So if we look at the mean, it was around 0.02 seconds. This is the flow completion time when we separated the traffic. And the standard deviation is also small. Whereas when you just mix everything into that router, you can see how large these values can get. Another use case was if we want to apply some cybersecurity in our network, how can we mitigate the SYN flood attack? SYN flood is just an attack where a certain attack machine would generate a large number of SYN requests with spoofed IP addresses. And these requests are sent to a target server such that this target server would be overwhelmed and it would be unable to respond back to legitimate traffic. So we also developed an algorithm in P4 just to count the number of SYN packets per second. So this is all happening in the data plane. And then this value, the count of SYN per second, will be sent to the control plane where we are implementing the random early discard. And the idea is we would have two thresholds, activate and max threshold. If we are below the activate threshold, we don't drop any packet. As soon as we start exceeding the activate threshold, we start probabilistically dropping the packets. And when we get to the max threshold, we always drop the packet. This method is common. It's being used in firewalls, next generation firewalls. So we decided to see if we can implement it with this approach, especially that we have more flexibility in adapting those thresholds, making them more dynamic. And at the same time, if we have a firewall, we can basically offload this feature and have our programmable router, non-programmable router, sorry, have it drop these packets. So we generated some flooding traffic, so SYN flood attack. And every 2 seconds, the attack rate increases. And the values that you see here in this graph are measured on the receiver side, which is the victim. And what we can see is that this line here represents the activate threshold. This is the max threshold. And we started pushing data. You can see the receiving rate increasing. Now, when we get to that threshold, we start probabilistically dropping packets when we apply our solution. Whereas if you just keep it, it's going to keep increasing and basically consuming the bandwidth in your network. And same thing can be seen in the CPU of the receiver, which now is being controlled well. When we get to that point, so all the SYN packets are being dropped, and basically we get a very small CPU usage. Now, this is just because how this the mitigation algorithm works, but it's certainly not the only way. There are other ways that we can basically mitigate these attacks. And finally, we have an attack on DNS amplification, and how can we mitigate it in P4. So the DNS amplification is an attack where a large number of DNS responses are sent to a victim machine. And typically the attacker would send the DNS request and use the any keyword when sending that request. This way, the resolvers will try to get as much information for that zone as possible and maximize the amplification effect. So if you are sending a request with 64 bytes, you will receive like a response, let's say, of 3,000 bytes, around 3,000 bytes. And this depends on the website that you are querying and other factors as well. But the idea is you can send a lot of requests to these resolvers, and these are going to be generating large responses to overwhelm the target victim machine. So how can we detect DNS amplification with P4? Also, we use the tab here. All these packets are the DNS responses that were sent without a matching request. So imagine receiving a lot of DNS responses, but you didn't have any device in your network sending DNS requests for these responses. So this would be a little bit suspicious. And what we are doing, we are getting these traffic, identifying them into the P4 program, counting how many DNS these DNS packets are being received per second per reflector, because typically, they would try to leverage those public reflectors. It can be a large number, it can be a small number. So we want to track how many of these unmatched DNS responses we have for each reflector. And also we are computing the amplification factor, which basically tells us how large these responses are compared to the requests. And then we are sending this information to a server where we are running a machine learning algorithm just to identify some thresholds in time series. And basically, if we have an amplification attack, if the algorithm tells us, okay, it's there. So what we do is we construct a rule. We use here the multi-field classifier, and we say that we want to drop the traffic if they have the source IP equal to that of the reflector. At the same time, if the length of the DNS response packet is greater than some threshold. So by having also a match on the length, we can basically allow the legitimate DNS responses, let's say sent from Google public DNS, they would still be flowing back into our network, but only those that are large would be stopped. And again, this is always, there's a control loop here. So as soon as this attack stops, you can basically refine your configuration rules and push them to the non-programmable router. Some tests that we did, we have traffic from Qaeda. We replayed this Qaeda traffic. You can see it here in green. This is the rate. And on the x-axis, you have the time. So for the first 60 seconds, we didn't activate the mitigation. And we started the attack here at around 30 seconds. And what we can see is that this DNS amplification that we generated and had a rate of more than 10 gigabits per second, it immediately flooded our network. And we can see here the share of these reflectors that we used. So we have 4 reflectors generating this kind of, or this rate of DNS amplification attack. And then for the remaining 60 seconds, so this is where we activated our mitigation. The attack starts at this point here, around 90 seconds. And you can see here, as soon as we have this spike, the attack was detected and blocked. So we were able to stop this 10 gigabits per second attack in less than 1 second on a legacy router. Some observations that we've seen regarding this approach. First, it is cost efficient because the framework is cost efficient because basically you would need some taps and a P4 switch, a programmable switch. And both of these are relatively cheap. You can get both of them in less than $10,000. And another observation is that while we are not applying the configuration rules at line rate, we are having the switches processing these packets at line rate and using whatever statistics or intelligence that we have to apply these configurations. Many times you would see people, when they see like a solution that is not doing things at line rate, they think that you're waiting tens of seconds or having net flow or, do things offline. But this is not the case here. We are doing packet processing in P4 switch at line rate and then immediately modifying the configuration and the legacy device. We've seen that this kind of framework can work in plenty of applications. Some examples, you can do traffic rerouting, load balancing. You can, for example, get the measurements from these links at line rate, have your optimization algorithm that will tell you this is how you should separate your traffic. Traffic steering, you can also get fine-grained measurements and telemetry. So we can tap on your routers, get the queue statistics, and there's a paper that already did something like that. You will get a very granular visibility on your queue. However, this framework cannot, or we can't have applications that basically send feedback to the clients. So there is a very well-known P4 application called HPCC. This is a congestion control-based application. It will measure some features in the network, some characteristics, and then it will send back to the client to regulate their sending rate. And because here we are deploying things passively, we can't have packets being injected and sent back to the client. Although you can augment this design and maybe have a certain link that would allow you to send some packet to be received at your clients for feedback. As a conclusion, so we demonstrated P4Tune, this framework that allows us to leverage the power of programmable data planes in a legacy network. The idea is we don't want to replace the whole legacy network, but we want to still benefit from the power of these programmable data planes. We are using them not for forwarding, so we are keeping the forwarding similar to what you would do. So there's minimal changes to your topology in terms of routing configuration or IP addresses. It's completely passive, so we don't need to care about any of these. We would have some algorithm in the control plane or in a server coming up with rules, and these rules will be pushed to our legacy devices. By doing that, we are creating a closed control loop that allows us to measure and modify. We showed 4 use cases. 2 are related to quality of service. These are the dynamic buffer sizing and the flow separation, and 2 that are related to cybersecurity. For future work, we are planning to implement further applications using this framework and possibly test them in a more realistic scenario, probably in a production network. Finally, we would like to acknowledge the NSF. This project was supported by the National Science Foundation. And that's it for the presentation.
All right, well, thank you so much, Elie, for going over a lot of that. I'll put out the call for questions. If anybody does have any questions that they want to ask, please use the chat room and I'll relay them. I have a couple to sort of start us off here. So you said that you're still trying to target if it would make sense to try to deploy this in a more production environment. Right now, just sort of thinking about what would make the most sense. Are you thinking more along the lines of a campus or more of a regional ISP? What would a production deployment look like in this case?
I think if we are talking about like if it is possible, it would be possible in both. We would want to see here which deployment is more easier to convince the operator to test it. I think probably the campus network will be a little bit more challenging, but
Elie, I will add to what you are saying. We're planning to do in the campus network here at USC is a little bit difficult. Let me call the enterprise network, but we're implementing this idea in the Science DMC, not the algorithm yet, but we deploy already the sensors, the passive tab and the P4 switch. So our idea is to try to implement in the Science DMC at USC. That'll be our first target. We did try to implement some in the campus, and that's a little bit more challenging.
Yeah, that's where I was kind of going with it, is if the enterprise group would have an appetite for doing something like that. And I know that you guys have talked with and worked with Princeton a little bit, because I know June has had some luck in getting things deployed on their network as well. What would be sort of the big selling point to a campus operator if they were to sort of go down this road? And you know, I don't mean to dig too deeply into this topic. I'm just trying to think of ways that others on the call may try to sell this to their own infrastructure providers and or campuses. You know, what is the thing that this would get you as a campus provider versus sort of a more traditional network deployment? Is it really just the visibility, or is it more the control aspects?
I will get my opinion, and then I will let Elie, and certainly the audience, if we would love to hear about that, other thoughts. But when we talk about with the people in IT that manage the enterprise network, always the privacy is a concern, and therefore it's difficult. That was a challenge that we had. What was the idea? Our idea was to try to characterize the network of the campus network. We want to characterize how it looks, if we can identify early type of attacks. That would be one use case, similar to what Elie presented. But yeah, there is a challenge that is beyond the technical characterization of the network. Then there are more challenging, at least, for example, Elie talked about the buffer sizing. That's something that I'm confident we will do in the Science DMC. Now, that will be much more challenging to do in the enterprise network, because not the technical aspect, more the human aspect, the IT aspect. I should say, though, that in the Science DMC, we work very closely with research IT, and research IT at USC is willing to try these ideas more than the personnel in the campus enterprise network. Research IT managed the Science DMC, which is only for researchers. Enterprise network has all sort of traffic, including students, the dorms, et cetera. So that's why it's going to be a little bit more challenging to convince. That's the input that I can give. I don't know if Elie, you have something in mind.
No, that's it. I think you said it perfectly.
Okay. So certainly others on the call chime in if you have any opinions about how this may be deployable within a campus or even regional networking environment. I know a lot of the names that I recognize here, you've looked into this in some way, shape, or form. I guess my next question is more of a functional one. And I see that Geronimo responded, so let me do Geronimo's before my question. Amlight is always interested in running a POC. We have the switches and taps, so that may be an option for you guys if you want to reach out. Geronimo, maybe just slap your email address in there, and that way they can contact you. There you go.
Thank you. That would be great. And yeah, Geronimo, I'm sure we will be in contact. We will contact you. We're very interested.
So my next question was more of a functional one. I think you said that the brand of switch you were using earlier, but I did not write it down. What was the variety or vendor support right now for this?
So for this non-programmable router.
Well, yeah, the non-programmables, but right now, what is the hardware support for Well, let me ask it slightly differently. What major manufacturers right now are supporting P4 on their devices?
That's an excellent observation. From my side, it's we use the Edge core, which is I don't know if the support, very little support in my opinion, because it's a white box and it's all about what you put in the data plane in your code. The good thing about Edge core is that if you go over the training that is offered by Intel, you can apply almost immediately what you get in the training. But in terms of support, there is very little because it's really a white box. I will let Elie add anything that he wants to add.
Yeah, it's basically, as you were saying, like you are developing those custom functions in the data plane. You know, they can be potentially with bugs, or you might have some logic that you thought that it's gonna work, but it's not really working in your current deployment. And the support that you're gonna get basically is maybe, you know, you can go to this forum that Dr. Jorge was mentioning and look at how you can fix your P4 program for a specific thing, but you're not gonna get like a support that they will troubleshoot the program for you and rewrite the program for you and give you like the fixed version of that program. So I think that's like the challenging part in it. And if you want to deploy these, let's say P4 switches in a full production network, as you know, the only switches there, it's gonna be challenging, and it's gonna be, you know, because it's source of errors. Once the error happen, you're gonna be in a very big trouble. You know, not like the other routers where they have support from vendors. You can easily change the configuration and they should work. Here you are changing the whole processing at the low level at the data plane, basically.
Okay, so right now the support is still limited to Edge core, which is that what Barefoot became? Or no, that Barefoot was purchased by Intel. I never remember the lineage of these things. Okay.
Mm-hmm.
But right now, that's kind of the only game in town, right? Or are there a couple of others that are sort of emerging? I guess where I'm going with this is, are we going to see a little bit more proliferation or adoption, or are people just sort of waiting and biding their time until somebody else decides to do it, and then it'll start to become a little bit more common?
You have multiple switch vendors, so EdgeCore is one of them, but there are other companies. They would be using, most of them are using the Intel Tofino chip. So it's like the support that you get is from Intel itself and not from EdgeCore, if that makes sense.
And what I will add, Elie, you are referring to the support when developing your P4 source code, right? Because you might have some support if I'm just making assumption here. I don't know how it works, but I see that there are some vendors that use this chip inside their switches. I don't know what support they offer. We don't have experience on that. But at the source code level, if you have questions, doubts, etc., the best way would be to go to the Intel forum. That's the type of support that I'm thinking.
Okay. David has his hand up. David, I'll unmute you. I think I can unmute you.
Yeah, so I was just going to throw in there, the Intel Tofino is really the only game in town for an accessible ASIC in the multi 10 gig, multi 140 gig platform right now. Arista uses it in their platform, but my understanding is users are not able to modify the P4 code on that. Cisco leverages P4 on their Cisco One silicon, but I have not heard of anybody that has actually modified the code on that, or that Cisco has worked with them to open up the P4 for end users to modify. So as of right now, it's really Tofino on basically the generations coming off of Barefoot.
That's really helpful. Thank you, David.
Thank you, David. Yeah, very helpful.
Thank you.
Okay. And then Ken also put in the chat room a list of people who are currently supporting it in some way, shape, or form. So yeah, there's some names there I recognize, and then others I've never heard of before. So I guess we'll start to see these things proliferate a little bit more. I guess the last question, this is more of a vested interest question. I see Joe on. Joe, I won't put you on the spot, but is this something that the performance telemetry group has been looking at a little bit, or is this anything that resonates with you that you'd like to consider for future demos? If you want, I can unmute you. Otherwise, you can just remain anonymous and answer later on.
Thanks. Thanks. I mean, I think it's there's definitely interest here of, I'm not sure from the whole group. I think that this is an interesting approach, and I was trying to think through it a little bit more on how one could apply it, specifically in the Science DMZ for helping with the security posture, as well as just having some straight out telemetry feedback. I have to ponder it some more. It's a very interesting approach.
All right. Well, thanks for your thoughts on that.
Thank you, Joe.
Thank you.
We were thinking about that exactly too, the security. If the P4 can help enforce the security policies of the Science DMC, that's what we're planning to do.
All right. Well, I think that we may be out of questions. So thank you again for presenting this stuff. As always, you guys are always right on the cutting edge and doing some interesting things. And we'll certainly look forward to hearing if you're able to get any larger deployments done in the future. And Elie, just send me a copy of the slides when you get a chance, and I'll make sure that this gets posted. And then for those that are still listening, we had a little bit of a schedule change in the last couple of weeks. Because there is a new CC star solicitation listed by the NSF, I was able to twist Kevin's arm to come in and give a talk next week. So Kevin Thompson from the NSF will give a brief overview of this most recent CC star solicitation. For those of you that have read it, it's a little bit different than previous ones. So he agreed to come in and sort of explain A, why it's different, and B, what's sort of around the corner and in the future for this program. So I'll send out the announcement about that. Hopefully people can join. Otherwise, we'll see everybody soon. Hope you all have a good weekend. Talk to you soon.
Thank you.